Hello everyone, this is Shimon Yu from Georgia Tech. Today is my great pleasure to be here and to share our recent progress on the NeuroSim benchmark simulator. So this is our in-house simulator to benchmark the different design architectures for the computing memory with various device options. So this is the motivation for us to develop this simulator to evaluate the hardware accelerators for artificial intelligence applications. As you may know, the machine learning is becoming more and more popular these days, and the AI applications are prevailing in our daily life. But the AI applications are very computational and data resource demanding. Therefore, we have to develop the hardware accelerators for efficiently process those workloads. So here, as you know, GPU is still dominating the market in the training, especially in the cloud environment. And we do see that FPGA is becoming a popular candidate for the inference, especially it can be reconfigured for fast prototyping. But the GPU and FPGA are based on conventional von Neumann architecture with a digital design, and therefore the energy efficiency is rather limited if we look at the teraops per watt, essentially the throughput divided by the power. Then the GPU is around 9.1. And then the trend is to develop the digital ASIC to further accelerate the machine learning workloads. And in this case, TPU stand out as one of the promising candidates here. And this rely on the fixed point MAC operation in the systolic array. And the energy efficiency can be boosted to a few teraops per watt. But if we want to further increase the energy efficiency, then we have to employ some of the mixed signal analog approach. And in this case, we try to merge the computation into the memory array to reduce the data movement. And if we do that, the expected energy efficiency can be like 10 to 100 terawatts per watt. Of course, there will be some concerns regarding the precision requirement for the mixed signal and analog approach. This is because the mixed signal and analog approach naturally suffer from some noises or operations. Therefore, the accuracy at the system level may be suffered from degradation. So we're going to address those issues by the hardware and software co-design, and we will highlight some of the efforts in later part of the talk. So here we believe that the computing memory will first be used for the edge inference, where the model is pre-trained. And in the future, if we can also support the incremental learning, then that will be some add-on features for the computing memory chip. But I don't believe that at this moment, training from scratch is an appropriate application scenario for the computing memory, especially at the edge. All right, so then let's review some of the basics for the computing memory. And essentially, this is a mixed signal compute scheme where the neural network model can be mapped to the memory array. So for example, here the input features can be mapped to the voltages that are applied to the memory array. And we can turn on multiple rows simultaneously. And then the weights of the neural network can be mapped as the conductance of the memory cell. So if we use the input voltage multiplied by the conductance of the memory cell, we result in the element-wise multiplication between the input and then the weight. Then we get the dot product here. Then this current can be naturally summed up along the column. Therefore, we can perform the accumulation along the column. The output from the column will be the analog partial sum, and then this one can be further digitized through the peripheral circuits, for example, the ADC to convert from the analog domain to the digital domain for the further processing.
有一个演讲。
For example, here, depending on the precision of the weights, then we may have to do the shift and add
如果你也有空，
array. This is because if the weight is like 8 bits, and if the memory cell is like only 1 bit per cell, then we may have 8 cells to reconstruct the significance through the shift and add. Then here for the memory cells, there are many candidates that can be used for the computing memory. We can use the mature like SRAM technology, and here we may prefer like 8 transistor SRAM cell to have the read and write decoupled paths. This is because here we may want to turn on multiple rows. Therefore, if we use the conventional 60 SRAM cell, then the cell may suffer from the read disturb because the bit voltage will decay to a very low level. Then the read disturb may happen. Therefore, 80 SRAM cell is better candidate here. And then we can also use like a 1T1R more compact structure here to represent the weights. So here the resistor can be the number of memories like R1, phase change memory, STT-M1. So basically those emerging memories which use the resistance to represent the state. And then furthermore, we may also utilize the 3-terminal transistor whose channel conductance can be modulated. And here in this case, we show the one transistor controlled like one FEFET, ferroelectric field effect transistor, as the weight cell. So here there are many possibilities to design the computing memory array, and then there are many technology choices as well. So here we just showcase the landscape of the emerging technologies, including the R1, multi-level state of the R1, and then the phase change memory, and also the FEFET, and also there are even emerging new material-based electrochemical random access memory. So there are many design choices here. And then on the macro demo side, we also see a lot of recent demonstrations, at least at the sub-array level, or maybe a few array level. For example, here there are many demonstrations using the SRAM and modify the bit cell for the SRAM. And also here, this is from TSMC, and this is at a very advanced technology node. And then the R1 has also been integrated into like a megabit level array. And then 1T1 R1 can support the computing memory as well. So here, there are many design choices from the device technology point of view. Therefore, there is a critical need to evaluate the system level performance with those new devices with many macros, because here most of the demonstrations is just with one macro with only one subarray. So therefore, we need some simulator to predict the system level performance. So that's the motivation for us to develop this open source simulator for the computing memory architecture. And we name it NeuroSim. And this essentially is a pre-RTL simulator for early stage research for the design space exploration. So this is not SPICE simulation. This is not the synthesis or the physical design. So this is a pre-RTL like high-level simulation. So here we have this GitHub link, and we periodically update and maintain the website. So we have multiple versions of this tool, and I will introduce some of the features in the following slides. So this is a brief history of this tool, and actually the first appearance of this tool can be dated back in 2015, and we presented a poster at the workshop. So this is the first time we use this name, NeuroSim. So at that time, it's basically a second level simulator for some basic neural interrupt. So here, the initial version is like a two-layer, fully connected multi-layer perceptron. So this is the initial framework application, just a simple network, and this was presented back in ADM 17 and followed up by the TCAT 18. And then later we realized this is a very small model. Therefore, we have to interface with the machine learning packages to define arbitrarily large models. Therefore, we choose to interface with PyTorch using a Python wrapper. And then this results in the first version of the DNN plus NeuroSim. And the first version focused on the inference, and this is presented in IEEE 19. And then we also expanded the NeuroSim for the on-chip training, and then this was appeared in the TCAT 20. So I would like to thank many of the students who have contributed to this project. So next, I will show some of the impact of the NeuroSim family. So as registered in the GitHub, we have like more than 300 users, and most of them coming from university and with some industry and research labs as well. And here are some of the companies we have visited, have used our tools. I listed here, and also universities. And then resulted publications more than 100. So there are like I believe more than 200 citations of the tools so far. All right, so let's talk about some of the technical details. So let's first look at the methodologies of this simulator. And it was coded in C++ and then wrapped by the Python. So here, this is an end-to-end framework, and we support the inference and also online training, and also recently we have done some 3D version of this design as well. So here we basically have input parameters that control the device features, circuit topology, and architecture, hierarchy, and data flow, and also different algorithms. So then the output from the simulator will include the algorithm level performance, that will be the inference or the training accuracy, and then also the hardware performance and metrics like the throughput, energy efficiency, and like computer density, like TOPS per millimeter square. So first of all, the algorithm level accuracy is based on this WAG quantization method. So this is a hardware-friendly quantization method for quantizing all the parameters in the software codes, including the weight, activation gradients, and error. And so here in our implementation, we also added like the partial sum quantization. This is because the ADC may have limited precision, and then the subarray, its output needs to be quantized as well. So this is in addition to the original WAG method proposed by the algorithm researchers. So here we can support different kinds of network models arbitrarily defined by the user, and then we can support like the CFAR or ImageNet kind of data sets. And then the hardware metrics are based on the analytical models, but those models have been calibrated with the SPICE at the module level, and will provide massive options and like technology nodes from 130 nanometer down to 7 nanometer, and the model transistor parameters like the on current, off current, threshold voltage, and so on are calibrated with the PTM model. And also we did some minor changes to the PTM model because some of the predictions deviate from the industry trend, and we calibrate with some of the foundry data in the recent like let's say 14, 10, and 7 nanometer node. And then we can choose different memory technology and then change their parameters and different ADC option as well. So the analog modules like the ADC are calibrated with the cadence simulations. So this is based on custom design. And then the digital modules are estimated with the standard cell design, including like cell area and logic gate delay, dynamic power, and leakage. So those are basically based on the equations. I will show some details later. And then also we consider like interconnect modules. So because there will be parasitic RC delay and power along the wires. And for the data flow here, we just use a simple H-tree routing. So first, let's look at the methodologies for the area estimation. So for example, we have to define the memory cell type, and then we will consider whether it's a 1T1R or it's a crossbar array. And then we will get the array size by the input parameters like the cell size in normalized to the F square. And then we will define the array size, then we can get the array area. And then this will be the core of the array. Then we will define the peripheral circuits. So for example, we have to define the switch matrix and the decoder specs. And then we have to consider the mux, depending on the current that needs to be flowing through the mux. This depends on the right current of the cell. And then we may have to size up the transmission gate to avoid large IR drop along the bitline mux. And then we have to look at other like ADC area, because ADC typically takes a larger area, so we have to share one ADC with multiple columns. So there will be like a mux sharing for the ADC as well. So then we have to look at all the possible like dimensions of those design, and then we have to do some folding of the area. I mean, for folding of the layout to save some area. So on the latency side, then we look at, for example, the rate critical path, and then the RC delay is estimated by the technology files. For example, the on-state current, of course, will determine the equivalent R, and then we will get the parasitic C from the loading caps, from all the transistor cap and then the wire cap. And then we are going for this is for digital block, and for analog block it's tricky. So therefore we directly try to simulate multiple design points using the cadence simulation, and then it will be a fitting function from the simulation, SPICE simulation. And then we will consider the operation scheme and find out the critical path. And sometimes some of those operations can be done in parallel, for example, in a pipeline fashion, so we can hide some of the latency. For example, when you do the colon row decoding, you can do the colon decoding at the same time. So then you can save some of the latency. And so basically, we are going to look at the critical path that is typically from the arrays like input from the row, and then you go through the decoder, and then drive the go through the driver, and then the RC delay for the word line, and then the cell activation, and then the bitline RC delay, and then the mux and the ADC sensing delay. So that is typically the critical path for the operations, because the other peripheral logic can be run at faster clock frequency, and the critical path will be this analog path from the row to the column, from the row input to the column output. And then the energy estimation for the digital part is mostly the CV square kind of dynamic energy, and we are going to get all of that, sum up all of that, and then the digital blocks also CV square, and then the analog blocks again is a fitting function from the cadence SPICE simulations. So those are the methodologies, and then let's look at some of the organizations of the tool, and then we will show some of the sample results. So here, this is an overview of the tool. As we discussed earlier, so the on the algorithm side, it's in the Python environment, and this is based on the PyTorch. So we can define arbitrary neural network model, and then here for the inference, this is version 1. Then we will consider a few non-ideal effects from the hardware to evaluate the inference accuracy degradation. And for example, if the weight drift over time because the resistance may drift over time due to the retention degradation, then the accuracy may also drift over time. And also the ADC may have the limited quantization and precision. Therefore, we have to consider the partial sum distribution and then maybe use nonlinear like ADC quantization to quantize the partial sum. And the ADC precision will matter for the inference accuracy. And then this is on the algorithm like accuracy side. If you want to get hardware metrics, then we have to do this like trace-based simulation. So here we are going to export the neural network structure to the hardware like chip floor planner to basically distribute the weights into multiple tiles, and then consider the weight mapping strategy. And so basically the input feature map and the weights are tensors, right, like a 4-dimensional matrix. And we have to unroll that to the 2-dimensional memory array. So there are different ways to do the unrolling. And then we're going to discuss some of them in the next few slides. So there will be some data flow design considerations. And after that, then we're going to map the weight to the conductance levels of the devices. And then, of course, we may have to take care of the negative weights. There are different ways to do that. For example, we can use like the maximum conductance represent the positive one, and the minimum conductance represent the negative one. And then we can have a dummy column for the array to represent the 0. Therefore, all the partial sum needs to subtract the dummy columns outputs to basically reconstruct the negative weights. And also, if we have the binary cells, we can do the tooth complementary code to deal with the negative sign. And then we can map the neural network into multiple arrays and multiple cores. And then eventually we can have this hierarchical simulation because the neural network may be very large. Therefore, we have to partition one chip into multiple tiles. And then multiple tiles partition that into multiple processing elements, and then one processing element needs to be partitioned to multiple subarray. So here we show this hierarchy again, and at each level there will be the input and output buffer, and then, for example, at the PE level, we have the subarray, and then there will be an adder tree to accumulate the partial sums and then go through the buffer. So this is a hierarchical structure. And then within the subarray, we support 3 kinds of subarray. The first one is SRAM, and then the second one is 2-terminal cells, for example, 1T1R. And then the third one is this 3-terminal cell, that is like 1T1 FEFET, or you can be like a flash transistor as well. It's basically 3-terminal device. And then we have all the peripheral circuits built in, like the ADC, switch matrix, and shift and add, and so on. So here, for example, we can do some system-level benchmark using by varying the array size, if that is your design variable. Then we can look at the trade-offs between different array size to implement the same VGG8 network, and with the same device option, like each device can store like 4 bits per cell. And here we can also vary like ADC precision to look at the trade-offs between like the accuracy and throughput and then energy efficiency. Of course, then the general trend, as you may expect, with higher ADC precision, then we can get better inference accuracy. This is on CIFAR10 dataset. And then depending on the array size and also the memory bit cell precision, then we may need different precision of the ADC. But the general conclusion here is that for reasonably good accuracy, then like 5-bit ADC is necessary. Then, speaking of the ADC, there are multiple choices. And here for the voltage mode-based ADC, we can have the SAR ADC or the flash ADC. And SAR ADC basically have one voltage sense amplifier, like comparator, and then there's a SAR logic with a DAC array, and then we can sequentially compare the bitline voltage with the reference array. And of course, this will have a smaller area but longer latency. And the flash ADC is straightforward. We have multiple comparator or SA, and with different references, and we can compare all of them simultaneously. But this one is the exponentially increasing number of SA with the precision. So the trade-off is very clear. Here, the SAR ADC is preferred if the precision is more than 4 bits. And then this is because if the precision is high, then if we use a flash ADC, although it's fast, the energy and area will exponentially increase like this. So it's not very efficient. And then beyond the multi-mode ADC, we can also support the current mode SA. So this one is a current mode SA, and then we can have different reference currents and for the multi-level sensing as well. We briefly talk about this point. We need to consider the weight mapping and duplication possibly. This is because, as we discussed earlier, the input feature map will be a it's like 3-dimensional tensor. And then here we have to unroll it. And then the kernel, for example, here will also need to be unrolled. And the conventional mapping is a very straightforward way. So basically for the kernel, like k by k kernel, and with number of D channel, we're going to unroll that into a long vector that occupies the column. And then the input feature map will be scanned over with the same dimensions of the vector. So then we can get the output vector in sequence as well. But if we will do that, then the array size may be very large. So we may have to cut that into small array subarrays. But the conventional mapping has some disadvantage because the input cannot be efficiently reused. Therefore, we propose so-called novel mapping. So the idea is that we just unroll one element in the kernel. Let's say this, for example, 3 by 3 kernel. We only have the first element, and then we have number of D D elements, D channels. So we only unroll this one more like a kernel, one element into one array, and then for different kernels, we are going to use for different elements in the kernels, we are going to use different subarray to do that. Then this we need to add up the partial sum from the subarray. But the good the advantage of this novel mapping is that the input feature maps can be reused efficiently and can be basically transferred to the neighboring PE in a systolic fashion. So we can reuse the input features as much as possible. So this is the good feature of this novel mapping. And then another thing is that we may have to duplicate the weight. This is because in the first few channel layers of the neural network, typically the input feature map is very large, while the weight, the current number of weights in the kernels is less. Therefore, the bottleneck, if you look at the whole pipeline of the neural network, then it will be much slower at the input stage because we have to go through a large input feature map with a small number of kernels. Then the idea is that to duplicate the kernels, if we have enough memory space, then we can duplicate the weights. Therefore, we can process the input feature maps in parallel. So if we want to design a pipeline stage, And this is a must because we have to make the pipeline stage, the latency somehow matched between the shallow layer and the deeper layers. All right, with those considerations, so here we just want to showcase some of the examples with the benchmark. So this is to benchmark 8-bit VGG8 network across different technologies. And so here we consider two technology nodes, like 22 nanometer, because most of non-volatile memory are integrated at 22 nanometer node today. And then of course, SRAM, you can have 7 nanometer or even 5 nanometer or 3 nanometer, but we don't have the parameters for that in the simulator. So the best we can do is 7 nanometer. And then we can consider different like ADC precision and then cell precision. And then the important parameter here will be the on-state resistance of the devices. So like the RRAM and or the phase change memory or the ferroelectric devices, then the on-state resistance will be very different. And that will be translated to the energy efficiency as well. So here with the benchmark, then we can get the area of different designs. And of course, 7 nanometer SRAM is still smaller because the technology node is more advanced. So the peripheral circuits can be more compact. And the energy efficiency wise, here you see that the non-volatile memory generally can be good, assuming that the on-state resistance is high enough. But if the on-state resistance is only a few kilo ohm, then the energy efficiency may not be as competitive as more advanced SRAM. So here the point is that we have to improve the energy, and improve the resistance of the technology. But this benchmark table assumes that the activity of the inference is 100%. But in the edge application, most of the time, maybe the device is in the sleep mode. Therefore, here we consider the computation ratio versus the standby ratio. So one means the chip is always running, but then if we reduce the computation ratio, that means the chip is more in the sleep mode. If you do that, then you will see that the SRAM and is this black curve, and all the non-volatile memories are here. So then the non-volatile memory actually can outperform the SRAM if the device is standby frequent. So this is because SRAM is always leaking over time. So here are a few conclusions. The desired on-state resistance of the emerging non-volatile memory will be in this range. And then we prefer to have multi-level to beat the SRAM and more advanced technology node. And non-volatile memory will be more attractive for the edge device with no compute activity. So this is way 2, the version 2 for the online training. And similarly, we will have those Python wrapper. But here we are going to introduce more device non-linearity into the non-ideal effects into the weight training process. Using the weight training, it involves the write operation to the device. Therefore, we have to consider this asymmetry and non-linearity in the weight updates. And also we have to consider the device and the device-to-device variation and cycle-to-cycle variations. So we have to include that into the accuracy estimation. And also for the hardware side, for the training, we have to consider the back propagation for the error calculation. Therefore, we need to consider some transposable like array design to basically support both forward and backward propagation. And also the third step of the training will be the weight gradient calculation. So this is a convolution between the error and the input activation. And so this one, in our particular design, we use SRAM-based design for this gradient calculation. So then we have to add some more blocks to the training chip design. So let's talk about some of the training challenges. So here, this asymmetry nonlinearity is a well-known problem for the emerging non-volatile memory if we want to use it as analog synapse. So basically, the problem is that the conductance of the device may increase with pulses following the blue trajectory and may decrease the conductance follow the red trajectory. Therefore, this is a symmetry and a nonlinearity problem. So here we also analyze why this nonlinearity will cause the problem. This is because if we keep increasing the conductance and then somehow there is a negative sign of the weight, then if we have the red, we have to follow the red trajectory, it will drop significantly from this point back to here. So that means statistically, most of the conductance will be centered in the conductance range. So here we show that without nonlinearity, maybe the weight distribution is more uniform, but with the nonlinearity, then the weight are more centered around the zero. So this is not good. It will affect the training accuracy. So here then, to overcome this challenge, we introduce some momentum in the weight update. So that means with the weight update does not only depend on the current gradient, but also depend on the previous a few steps gradient. So we can keep the momentum. If the weight is going to increase, then we're going to keep that trend unless there is a big negative trend of the weight update. So here then we show the training evolution. So here the summary is on the right. So the basic idea is that with this momentum we can improve the training accuracy, but still, as you can see here, with the nonlinearity factor going up, then the training accuracy will degrade. So then this is still quite challenging to get that good accuracy if you have a nonlinearity in the weight updates. And besides the nonlinearity, then the device may also suffer from this device-to-device variation, and also each pulse may give you like cycle-to-cycle variations. So we have to incorporate that into the simulation as well. So then here are more results. So you can specify like the device-to-device variation like percentage as a standard deviation of that, and then you can see that with the different device nonlinear device-to-device variation like standard deviation, then the impact is not that significant. So here the x-axis is different nonlinearity. Still, the nonlinearity will dominate the accuracy. With the same nonlinearity, then the accuracy will be slightly affected by the device-to-device variation. So in other words, the neural network has certain degree of the tolerance with the device-to-device variation. But the cycle-to-cycle variation may hurt more on the accuracy. So here we show the cycle-to-cycle variation and impact on the accuracy. So if we change the standard deviation a little bit for the cycle-to-cycle variation, then the accuracy may quickly drop. So that means we have to control this cycle-to-cycle variation in the training process. And then here I will skip some of the details. You can also basically look at the training system performance and in the area breakdown, latency breakdown, energy breakdown, and also across different components of the chip. But I just want to point out that the energy consumption here is dominated by the, if you look at this pie figure, then this green one is DRAM. So this is a problem for the training. This is due to the intermediate data. Even you train like a 100 megabyte model, the intermediate data, like those arrows and gradients, those data's volume can be like tens of gigabytes. So there's no way that you can store tens of gigabytes intermediate data on chip. Like your global buffer, maybe a few megabytes or tens of megabytes. So you cannot store those intermediate data on chip. Then you have to store it on DRAM. But once you go off chip, then all the energy will basically be spent on the DRAM access. So here, even we use the LPDDR as the interface of the DRAM, then still the DRAM energy will dominate. So here, this is big table. I don't want to go into the details. I just want to highlight a few points. So here, on still play an important role for the peak performance. We want a larger on-state resistance of the device. And then the pulse width for the write operation should be minimized to like microseconds. Otherwise, it will hurt the throughput of the write or of the whole system because the training will be write intensive. And then we have to control those non-ideal effects, like the nonlinearity, cycle-to-cycle variations, has to be controlled under a certain degree to guarantee the accuracy. And also, like the S-run is a good candidate because write operation, then S-run is fast. And then for this F effect, particularly this F effect, actually is good because the write speed is reasonably good and the on-state resistance is high. But no matter what, if you look at the final energy efficiency, it's constrained to about 2 TOPS per watt, regardless of the device technology. This is because, as we mentioned earlier, the energy is dominated by the DRAM access. So this means that this training from scratch, as I said earlier, is not a good application scenario for the computing memory if we cannot solve the DRAM access issue. All right, so then let's look at some of the validation of the NeuroSim. This is what we recently have done. So we want to validate the prediction of a real chip. This chip is also designed by our group, and we thank TSMC for providing us the tape-out shuttle. So basically, we calibrate the NeuroSim prediction at the module level with this chip. So we can basically compare the area energy latency on the module by module with this chip. So we have to introduce some of the factors to basically compensate for some of the practical considerations in the real tape-out. For example, the transistor sizing, wiring area, routing area, and gate switching activity, and post layout performance drop. But if we introduce some of those estimate factors, we can get the estimated like the performance within like a error rate within 2%. So we can introduce some factors to compensate for those physical design related differences. All right, so then I will spend a few slides on the extension roadmap for the NeuroSim framework. So here we first make it reconfigurable because the initial version, the chip is custom designed for a certain neural network model. So recently we have introduced some of the reconfigurable modules to make the chip can handle different models during the compile time. So we can consider different data flow within the same chip architecture. And then second extension is to make it compatible with monolithic 3D. And then this is to basically partition the design between a memory tier and a logic tier. So the memories can be stacked on top with more mature technology node, for example, 40 nanometer, and then the logic peripherals will be at the substrate with more advanced like 7 nanometer node. And also we consider multi-tier like stacking with the TSV and hybrid bonding. And also we recently expanded the technology parameters at lower temperature, like 77K and 4K, to support the system to be operated at the cryogenic temperature for some high performance applications or the quantum peripheral control. And recently also we have expanded the framework to support the 3D NAND, because 3D NAND is the only technology that can handle the capacity of gigabyte or terabyte model for the language graph applications. So due to the time limits, I will not go into the details of each of those extensions. I quickly go over the slides. So then this is monolithic 3D. And I just want to point out on the backend, we prefer to have some backend of LAN compatible oxide channel transistor to serve as the logic process as a backend, because we need a low temperature fabrication of the backend, and oxide channel transistor can afford that. And then here, this is a heterogeneous 3D integration, so we can have multiple tiers stacked together. But in this case, the thermal dissipation may be an issue, so we have to consider the cooling technique to closely monitor the temperature of the system. So here we have some thermal model built into the simulator as well. And then this is cryogenic, so we have to recalibrate the transistor characteristics at lower temperature to update the technology files. And then this is a 3D NAND-based model. So here we can implement very large model, and for example, this language translation model, and then can be mapped to the 3D NAND. And then 3D NAND, of course, is not compatible with logic process. Therefore, we have to make those like ADC and then the digital blocks using the advanced logic process. But then we rely on the hybrid bonding to interface with the NAND die. So this is necessary. So in the last few minutes, I will just show some examples of running the DNN plus NeuroSim version 1.3. So if you clone our code from GitHub, then you can run it by yourself. We have the user manual on the website. And here I just want to quickly go through some of the key files you may want to take a look. So here, if you want to modify the parameters, there is a parameter CPP file. So here, first you can modify the device features. For example, here you can define the precision of the memory cell, and also you can choose which technology, like either SRAM or emergent non-volatile memory. For SRAM, then you can basically input the parameters of the SRAM, like a W/L ratio, and so on. And then for the non-volatile memory, you can input the parameters like on and off resistance, and the write voltage, read voltage, and so on. And then you can choose the technology node for the peripheral circuits, and also the wire width, and then define the subarray size, and then choose which type of ADC you may want to use, like the SAR ADC and flash ADC, as we discussed earlier. And then if you want to change the neural network model, then you have to go to this train.py file. But here in the website, I think we provided some of the pre-trained model, so you can bypass the training stage. And so if you download the default model, we have the VGG8 for CIFAR10, DenseNet 40 for CIFAR10, and ResNet 18 for ImageNet. So this is already pre-trained. If you run the inference-only simulation, you can bypass the training stage using those default models. But if you want to, so here, so you can change the like the weight, precision, and also the add non-ideal effects like the variation, as we discussed earlier. So this is with the default model, but you can define your own model, user-defined model. So then you have to create your own file on the model folder, and then you have to define the neural network structure use this make layer function. So basically, you have to create this file to define your neural network model structure, and this can be saved as a CSV file. So for example, the VGG8, you can define the layer structure like this. You can have your own neural network model, but then you have to train it. So here, this is workflow. Change the parameters in the CPP file and compile the C++ file. And then this part is to make your own model. You can skip that. And if you skip that, then you can run the inference.py file. So after you run the simulation, then this is a sample like output. It will give you the inference accuracy, and then it will also give you the floor plan, like which tile contain which layer of the neural network, and then report the memory utilization ratio. And then it will further give you a breakdown of the performance, like the latency energy, and then give you the breakdown across the different components of the hardware. And then at the system level, it will also give you the final energy efficiency, throughput, and compute efficiency. For example, those TOPS per watt, TOPS, and TOPS per millimeter square, those information at the system level. I think that's all for the tutorial, and I would like to thank the project contributors listed here, and those are my students. And also I'd like to acknowledge the support from the funding agencies here. And thank you, I would be happy to take some quick questions.